Determine if the series converges or diverges, where p is any real number. We have the sum from n equals 1 to infinity of n to the power of p times 0.5 to the power of n. Because we have a power of n, we will use the root test, which states, given the sum from n equals 1 to infinity of a sub n, with the limit as n approaches infinity of the nth root of the absolute value of a sub n equals L, if L is less than 1, the series converges. If L is greater than 1 or approaches infinity, the series diverges. If L equals 1, the test is inconclusive. Let's begin by setting up the limit, which in our case is the limit as n approaches infinity of the nth root of the absolute value of the product of n to the power of p and 0.5 to the power of n. Because n is always positive, we can drop the absolute value. Notice here, even when p is negative, n to the power of p will be positive. Let's also write the nth root using the rational exponent of 1 divided by n. From here, we have powers raised to powers, and therefore we can multiply the exponents. Notice p times 1 divided by n is p divided by n, and n times 1 divided by n is equal to 1. This gives us the limit as n approaches infinity of n to the power of p divided by n times 0.5. The tricky part here is determining what's happening to n to the power of p divided by n as n approaches infinity. Notice when n approaches infinity, the base is approaching infinity, but the exponent is approaching 0. This is an indeterminate form. Let's take a look at this limit on the next slide, and then we'll come back. Again, let's consider the limit as n approaches infinity of n to the power of p divided by n. Let's set this equal to L, change the order of the equation, and then take the natural log of both sides of the equation. On the right, we'll use the limit property where we can bring the natural log inside the limit. We can write the right side as the limit as n approaches infinity of natural log of n raised to the power of p divided by n. And now we'll apply the power property of logs, which is natural log of x to the power of b equals b times natural log x. This indicates we can write the right side as the limit as n approaches infinity of p divided by n times natural log n. Let's write this as a quotient as p natural log n divided by n. Notice now as n approaches infinity, we have the indeterminate form of plus or minus infinity divided by infinity. I say plus or minus infinity because we don't know whether p is positive or negative. But because of the indeterminate form, we can apply L'Hopital's rule, meaning this limit is equal to the same limit after we differentiate the numerator and denominator with respect to n. The derivative of p natural log n with respect to n is p times 1 divided by n. The derivative of n with respect to n is 1. We now have the equation natural log of L equals the limit as n approaches infinity of p divided by n. In this form, we can actually evaluate the limit where p is any real number and the denominator n is approaching infinity, and therefore the fractions get closer and closer to 0, and the limit is equal to 0. And therefore we have natural log L equals 0. But don't forget, we're looking for L, not natural log L. To solve for L, we'll have to write the log equation as an exponential equation. Remember, if we have natural log x equals y, this is equivalent to e to the power of y equals x, where natural log is base e, and a logarithm is an exponent. This indicates natural log L equals 0 is equivalent to e to the power of 0 equals L. Again, to form this exponential equation, natural log is base e, and to form the exponential equation, we work around the equal sign, which gives the equation e to the power of 0 equals L. And e to the power of 0 is 1, indicating L equals 1, which is the value of the limit. Now going back to our previous slide, we now know n to the power of p divided by n approaches 1 as n approaches infinity, and therefore the limit is equal to 1 times 0.5, or 1/2, which indicates by the root test, since L equals 1/2, which is less than 1, the infinite series converges for all values of p. I hope you found this helpful.